I think that works now. Yeah, great. So we start counting the parent chain, right? Which side is that going to be? Right from here. So we have 4 carbons in this parent chain. What is the base going to be called? Yeah, it's going to be bute. And are there any double, triple bonds on this thing? So it's going to be butane, right? And we have an alcohol. What carbon number is the alcohol on? So your total name is going to be, yeah, you can do butan 2-ol or 2-butanol. Okay, the next one. Where do we want to start counting from? So this one, right? Yeah, we start counting from here. So now which way do we go, right or left? Yeah, because left gives you a longer chain. How many carbons are on this chain?
5.
So it's a, yeah, it's a pentane. And there's an ol, so it's going to be pentanol. But there is a substituent. What is this substituent over here called? And what carbon number is it on? So your total name is going to be 2-ethyl, yeah, pentanol, or 2-ethyl 1-pentanol. Oh, this one's fun. So what's our parent chain? No, the phenyl is going to be a substituent. The thing with that is that once you have like this conjugated aromatic ring, you can't really make it the parent chain because you couldn't name it like cyclohexatriene, right? So that is just going to be its own substituent called phenyl. So what's the parent chain? Yes, just the methyl. So if we have a methyl and 2 substituents coming out of it, 1 phenyl and 1 alcohol, what's the name going to be? Phenyl alcohol. Wait, no, phenyl methanol.
Why couldn't it be phenol, like FENOL?
So phenol looks like this when the alcohol is directly attached to the ring. This position is the benzylic position where it is 1 carbon separated from the ring. So this could also be called benzyl alcohol.
Can you call it benzyl?
Maybe, I don't know. Let me Google that. No, when I Google it, it shows up as benzyl alcohol. Okay, so the last one, what takes priority here? We have an alkene and an alcohol. Okay, we have 1 vote for alkene.
Alcohol.
Yeah, the alcohol is going to take priority. So where do we start counting from? Wait, yeah, from the left, sorry. So what is each substituent going to be numbered? Yep. So we have 2-ol and 4-ene. What does the total name look like?
4.
That's exactly it, yeah. Great. All right, so now we're gonna go on to ethers. What do we remember about ethers and their IUPAC nomenclature? Yeah. Well, they definitely are a functional group. Yeah, exactly. Yeah, and there won't be a suffix for ethers. They'll be a substituent. But anyways, you remember, wait, did he go over like naming ethers at all? So how'd you name the first one?
Dimethyl's ether, ether.
Dimethyl or, yeah, diethyl ether. So basically you take the substituent on either side and then just put each one in alphabetical order and then ether. So here we have two ethyls, so it's just diethyl. What about the next one? We have a phenyl and a methyl, right? So what order is that going to go in? Yep. And the next one, we have an ether as a substituent. But first, do you guys remember how to name an ether as a substituent? It's alkoxy. And then what does the alk stand for?
Like you replace that with like methyl, butyl.
So like I'll replace those prefixes.
Yeah, because alk is short for like alkyl or alkane, something like that. So you just replace it with, I guess, the length of the alkyl chain that's attached to the ether. So in this case, what is the alkyl chain that is attached to the ether? Yep. Yes, it's going to be methoxy. And well, first, what's the parent chain? Yep, it's this pentane. And what position is the ether in? Yes, perfect. And the last one. So what takes priority, the methyl substituent or the ether?
Well,
The ether, since it's closer to this one.
Yeah. So I would start counting from this side. So we have our parent chain, which is a pentane, and our substituents, which are what? Two methoxy or, yeah, two ethoxy and, yep.
wait, why is it ethoxy?
Because this thing that's coming out of the other side of the ether is an ethyl group.
Oh,
Yeah.
so whatever is attached to the oxygen.
Mm-hmm. You know, because it's named alkoxy if it's a substituent, and you just replace the alk with like the number of carbons that are on this side.
So it's never really gonna be referred as alkoxy.
Yeah.
It's just like a name, but it is.
Mhm. Okay, but I'll give you a couple more. All right. What is the name of that lovely molecule going to be? We have an alkene, right, which is going to take priority over the ether. Or methoxy pent. I would do like one pentene. But yes, that is gonna be the name. We'll do one more. I don't have room. All right, this thing. How do we name this thing? What takes priority, the ether or the alcohol? So we start counting from which carbon?
Right.
Oh, what that? Okay. We start counting from there. How long is our parent chain? Yep, we have 4 carbons in the parent chain. 1, 2. Wait. Yeah. So we know we're gonna have 1 butanol, but this substituent, how do we name it? What's this group? Yes, it's isopropoxy. And then if this was like a tert-butyl, it would just be tert-butoxy. So we have 3 isopropoxy. Great, okay.
One second.
Yeah. Okay, I can move on from this. Or
Number 1, right?
sorry, what?
Number 1, 1, no.
Yeah.
There's no need for that one, right?
I think you don't have to. I just do it for like liability. Yeah. All right, so let's move on. All right, real quick, I will need the side conversation to like not happen that much because a lot of people can't hear it. Anyways, Roche didn't really do this, but it showed up on his exam last semester and he didn't tell me to get rid of it, so we might as well just do it. So does alcohol or an ether have a higher boiling point? What do you think? Yes, why? Yes. So the obvious answer to this one is going to be, yeah. Now for this one, do you remember the effect of branching on boiling points? Yeah, the more branching you have, the lower boiling point is going to be. So which of the two has more branching? Yep, so which one has the higher boiling point? Exactly. So this question, let's rank them. What is going to have the highest boiling point? Because it has, okay, thank you. AC. Okay, but number 1 is the highest boiling point because it has 2 H bonding things going on. The second one is going to be B because it's exactly the same as C except C has branching. So it's going to be lower than B. And then D is the worst because it's an ether and there's no H bonding. Okay, I really don't like this question, so I'm gonna get rid of it because it's technically a weak Bronsted acid, but it can also act as a Bronsted base. And it's also, I don't know if it's a stronger weak Lewis acid or base, whatever. I don't like this one because it can act as like literally everything. But what you should know is that it's a weak. And it's a pretty good nucleophile, which is why we use it as a nucleophile. So it's a weak acid. Do we know what the conjugate base of an alcohol looks like and what it's named? Yeah, it's O negative attached to something. Yeah. And what's it called? Yeah, it's going to be an alkoxide. And then the alk is the same principle as the ether thing. And this gets changed out for like methoxide, ethoxide, so on. This alkoxide is a pretty good base and a pretty good nucleophile. Generally, anything with a negative charge is going to be pretty basic and pretty nucleophilic. Okay, now we have a whole page of like acid-base stuff, but I don't think Roche cares, so we can literally just skip it all. But there is something important you all should know. So do you remember well, let me just draw them out. So there's a few positions for hydrogens that have special names and special properties and whatnot. And they're important to know. So the first one, anyone remember what that's called? Yep. And do we think this is an acidic position for a hydrogen or not?
Yes.
Yes, why? Yeah, because the conjugate base of that is going to have a ton of good resonance with the benzene. What about this second one? Yes, it's going to be allylic. So one carbon removed from the actual double bond. And what do we think allylic is going to be like? Acidic, not acidic? Yes, because, yeah. Well, all of these are going to be sp2. Actually, no, this one, I don't think it's, I think, yeah, the only real sp2 carbon would be the vinylic one, which is this one. But I think the change in the orbitals, like how that affects the acidity is like kind of small compared to resonance. So that's how we look at this first. Anyways, allylic is going to be acidic because it does have resonance. It's not as good as the one in the benzene because it doesn't have the full conjugated ring, but it's something. And the last one. Do you remember what this is called?
You just said vinyl.
Yes, I did say vinylic. And this position is kind of terrible. This is not good to extract the hydrogen from this position because you don't want a negative charge in that sp2 orbital. It doesn't hold the charge well. But anyways, knowing that, Or can I move on? Everyone copied that?
Word number.
Or not good, not good in resonance.
Huh?
Or not good, you meant not good in resonance.
Not good in resonance and acidity. And the conjugate base is going to be really unstable. But knowing that, let's talk about this. So we have a bunch of protons. Do I have to wait? No? Okay. So we have a bunch of protons. Let's start labeling their positions. So A is going to be what kind? Yep. And that's pretty good, right? What about B? How far is it from the double bond? Yeah, so that makes it, yeah. So it is going to have resonance for that carbonyl. What about C? C is vinylic because it's right on top of that double bond. And what do we think about D? It's allylic and, yep. And E, what do we think about E? How many carbons is away from the double bond is it? Yes, so it's
Just like a regular.
it's just nothing, yeah. So knowing that, which proton do you think is going to be the most acidic, the most ready to dissociate? Yep, it's D because you have the benzylic and allylic position, so it's stabilized by both of those. Both of those groups. Because once you have a negative charge on this carbon, you can do resonance with this benzene and also this carbonyl. So, yeah. About D. So D is one carbon away from the benzene, and it's also one carbon away from the double bond, and that makes it both benzylic and allylic. So you get resonance stability from both of those, both sides. So it's going to be the most. So as an acid, you donate a proton, right? And in its wake, you leave a negative charge, or you leave a charge. So what happens is that charge is going to get resonance stabilized by both groups. And because that proton is so ready to dissociate because it's so stable, that makes it the most acidic proton. Okay, so we can move on to the synthesis of alcohols and technical ethers. So what do you remember is the main difference between synthesizing alcohols versus making ethers? Yes, if you're making an alcohol, your nucleophile is going to be water. If you're making an ether, the nucleophile is going to be an alcohol. But anyways, we can start with the reactions and their mechanisms. I didn't give myself enough space to write the mechanism, so I'll figure that out, but that's fine. So the very first one, what does this reaction look like?
Acid, catalyzed.
We're making an alcohol, so we're adding water, so it's going to be acid catalyzed hydration. And you know you have that, well, not for sure, but really good hint is you have an acid at the bottom, which is your catalyst. And an acid usually has a lot of hydrogens, and if it's a really good acid, it's going to have a plus charge. Oh, do you remember anything he mentioned about this method? Well, it's going to be Markovnikov. And okay, well, in this case, I don't think we used like sulfuric acid, so it's not as strong. But if you are using like diluted or hot sulfuric acid, it is a little bit aggressive, so it could just go ahead and decompose the molecule. I think he really likes to distinguish between like what's aggressive and not, which is interesting, but it's good to know. Oh, let me just draw the other possible reagents. I'll like redo this chart because there's a lot more information that he said that I did give myself room for. So I'll just redo it as like a study guide or whatever, and then upload that. So don't worry. But what do we remember about this reaction? What is the regioselectivity going to be? Yeah, Markovnikov, which means, yeah. Well, technically it's the carbocation that's on the more substituted side. But either way you think about it, I don't think it matters. And is there any specific stereochemistry? Like, is it going to be a syn addition? Yeah, there is no specific stereochemistry, so it's whatever. And are there rearrangements? So what part of the mechanism is going to allow for rearrangements? Yeah. So if you're asking, does this, are the rearrangements possible? You're just asking, is there a carbocation step or not? And there isn't this one. I think it's the only one that has it actually. So knowing all this, does anyone remember the mechanism? Yeah.
Would the carbocation be for E1 or SN1?
Neither. It's just like a basic nucleophilic attack. So the alkene basically attacks the acid. It takes a hydrogen. Then the hydrogen is going to attach itself to this side. And then once it attaches itself, you get the carbocation there. Okay, let me try to just draw the mechanism, but really zoomed in. So in this case, would there be any rearrangements? Why not? Yeah, it's already the most substitute it's gonna be. So everyone agrees with this product, right? And it makes sense how we got there. I don't think that it's necessary to know the mechanism. It wasn't for West, at least. I know Roche likes mechanisms more. I don't know if he's gonna put them on your exam. But once again, good to know. Do you guys want to move on to the next reaction? All right. So looking at these reagents, what is the reaction name? What do we have here? Oxymercuration. Exactly. And this is what kind of synthesis? Is it aggressive or more mild? Yeah, it's mild. It's not, there's nothing that's really going to attack the molecule and just degrade it. Okay, so one thing I know Roche does is that for like oxymerc, demerc, and for hydroboration oxidation, he'll give you the reagents, but he'll only give you like one line. So you have to make sure you know like what each line of the reagents does. So you have to know the top line does the oxymercuration, then the bottom does the demercuration. So if you have no NABH4, you have to know what that is going to give you as a product. Anyways, let's fill this out. Do we have any regioselectivity? It's going to be, yeah, it's also Markovnikov. What about stereochemistry? There is none. And any carbocation rearrangements? So the thing with this reaction, you do have a partial carbocation thing, but it's not a full one, so it doesn't allow for rearrangements. Oh, did everyone get that? Can I start the mechanism? Okay. Okay, this one's complicated. It's not going to draw every arrow, but you know, I'll just draw the steps. Oh, and you should know that this group is what gets added. So if this changes to an alcohol, then you would get an ether. So does anyone remember this from Orgo 1, like what the partial positive side is going to go on? Yeah. The mercury, but on the carbon hydrogen thing. Like, since we're attacking this double bond, which side is the partial positive gonna go? Yeah. So it's going to look something like this. And now we have kind of an electrophilic carbon because it's delta positive. So now our nucleophile, our water comes in, it's going to attack that. And this gets deprotonated somewhere along the way. Now that we have this, we have our like mercurium intermediate or something. We can use NaBH4 as the last step and get rid of that. And then all this is gonna do is replace this thing with a hydrogen. So there you go. That's the mechanism for that. And oh, we have like 4 minutes. Anyone need me to zoom in or anything? Okay. Okay, and there's 3 minutes left. I don't think we're gonna be able to do hydroboration oxidation, but we can do one problem because we just covered the reaction for this. So the question is asking by which reaction mechanism does the following happen? And this is dehydration of alcohol. Actually, we didn't do this, never mind. Yeah, I'll do it next time. It's okay. We'll end 3 minutes early. Oh, let me pull up the sign-in thing if you came here late or whatever.
I missed a few things. But it was just this right here. I missed out
Yeah.
part.